Hi, welcome to the Cosmic Pie Podcast. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
So, Robert, let's make it a little less.
A little less cool in here.
Yeah, so it's extremely hot in this room today, so we're trying to cool it off as late as possible. But
Right.
speaking about that, Robert, did
Okay.
you notice what it's like outside today?
It's actually warm for North Dakota in February.
You got that right. It's almost like spring is on its way. I hate to
Right.
say that because then all of a sudden we'll get dumped on in snow or something.
Right.
3 feet of snow next week or something, right?
That's always the way it happens when it starts warming up, folks. But yeah.
And I did notice you can see green on some of the lawns around here already.
Mhm.
So that's a nice
See
sign.
buds on trees.
Yeah, so that's amazing. But we've had a really mild winter compared to what we have on average usually get, right?
It's kind of crazy, to be honest, how
And
mild it's been.
And it's nice on the energy bill.
Oh, it is. Yeah.
So there is that benefit.
Well, then again, I don't have to pay heat in my apartment, so.
Right. Yeah, but your landlord pays heat. So
Yeah, so he's
now
been-
will he reduce your rent?
Yeah, no.
Okay, well. Oh, I know what he would say, he or she. We just won't put it up as much as what we had planned.
Right.
That's how you get around that. Anyways, welcome to the Cosmic Pie Podcast. So we are broadcasting live here from the University of North Dakota in Grand Forks, North Dakota. As a disclaimer,
Yep. Well, our opinions are ours alone, not those of the Department of Physics and Astrophysics, the University of North Dakota, or anybody else. Just us.
in other words,
We're responsible.
if you don't like what we say, you just blame Robert and I, right?
Right.
We're totally responsible for it.
We're
What comes out of our
responsible for it.
mouths.
Yep.
Now, we do have a live chat function, so if you want to send us a comment or a question throughout the podcast, feel free to use that. We'll stop what we're talking about and then hopefully answer any questions that you may have.
Not instantaneously, I might note, but we'll get to it.
It takes us a while to see it, and then sometimes we get all excited and get into a topic, and then we look up and there's 5 questions staring at us.
Right. That hasn't happened yet, but hopefully.
Well, the more people that watch this podcast live when we're streaming it in real time, of course, the better it is for us.
Right.
And
I
if,
agree.
And if you do like this podcast, don't forget to give us a
Thumbs up.
thumbs up. And if you haven't subscribed, please do so. That way
Yep. Ring that bell.
You'll be notified when we come on live. But in case you forget, we are live every Tuesday, unless something goes on, like we're away watching maybe a solar eclipse that's coming up soon.
Oh, I didn't think about that. That's a possibility, yeah.
So that eclipse is April the 8th, which is a Monday, and the chance of us being back here on Tuesday is probably 0. So
Yeah,
at
very
least-
slim.
So for Tuesday, April the 9th, we will not be having a podcast.
Yep. Or if we do, it's because we got rained out, and we know where we're going.
True. So
Because I think we're planning on going to different places.
yes.
So
Yeah, the other thing we could do is broadcast live from the eclipse, but the logistics would be so
the logistics would
problematic
be
that
terrible.
we'd never be able to
Yeah.
get that figured out. So we will not even attempt that.
we'll talk about that.
Yeah,
There may be a way of doing it.
we'll see. Okay, so one of the things we like to talk about during this podcast is to keep up on the recent news that's happening that's related to astronomy, astrophysics, science in general, this sort of thing. Now, there's something that's happening very soon, in fact, 2 days from today, and this is our first topic of discussion. And this involves what's called the Odysseus lunar lander. So this was just launched a few days ago, back on February the 15th. This is made by a private company, Intuitive Machines. So people say this is the first time the United States is going back to the moon in 50 years. But to be fair, it's not the federal government itself.
Right.
It's a private company.
Yeah. And I got to admit, what's their interest? Are they looking for the possibility of helium-3 and fusion or what?
Well, imagine that you had a half-decently cheap mode of transportation to the moon.
Okay.
Could you get any customers around the world that would be interested in sending some type of science payload or package to the surface of the moon itself?
Absolutely.
So that's where you make your money. It's really no different than SpaceX providing launch services essentially to everybody.
I was just wondering if there was some, non-transport reason.
Yeah, that's the big. I mean, obviously a lot of universities and colleges and different governments around the world would be interested in a low-cost way of getting things to the surface of the moon.
I'd love to come up with a project to send a lunar CubeSat.
Yeah, you could do
essentially.
that. Imagine one that you can look up at the sky on the
Right.
surface of the moon.
Oh yeah, that'd be
You'd have
lovely
to
in and of itself.
just figure out a way to keep the dust off
Yeah.
the lens and stuff.
Right.
Right? You have some kind of a device that sweeps it clean once in a while, or I mean, you could use compressed air, I guess.
Right.
Geared up, engineered inside to make that surface of the lens
Big-
free of lunar regolith material, right? The dust.
Right.
So if you can do the
A windshield
engineering,
wiper.
yeah. Well, you don't scratch the lens, right? That's what I was
Oh,
thinking
right,
about
right.
there.
Especially since it's probably most of the regolith is silicate, so it's like rubbing quartz across.
Well, remember, we used to get old cameras, or I've seen old cameras that were packaged up that you get like in a flea market or something, like stuff that's from back, I don't know, in the 50s, 35 millimeter cameras. And a lot of times inside of the case,
Bulb.
yeah, it's a little bulb, so you can blow air across the surface of the lens so you don't touch it
Right.
directly with your finger or a cloth to scratch it.
Yep.
So if you could have that kind of little, setup like
yeah.
that, right?
Because I'm going to make a note of something. The reason also I asked about the reason, the commercial reason, because that's the only reason a private company would do such a thing, is because people go, oh, we can mine the moon. The moon is much lower in metals than Earth is. Earth's crust is, which is pretty low, by the way. So there's not much mining that could be done on the moon, to be honest.
You mean there's no cheese on the moon?
There's no cheese.
I was going to sell the idea to Wisconsin to see if they want to.
That said, there may be tardigrades on the moon, but there are no cheese. Bad rock.
Now, you might be interested, where's this lander going to land? So it's scheduled to land on February the 22nd, so this Thursday. So it's approximately, I think it was like 5:30 or around
Something like
there,
that.
p.m. in the afternoon, our time. So it's heading for a crater, Malapert A. So on this bottom right image that you see of the moon, Malapert is a larger crater that's down on the lower part of the image. Just sort of most of it is off the image itself. But above that, you'll see a bunch of little small craters with lettering like A, B, C, and so on. And so A is the one that's the target for this lander. Now it's interesting because it is located at about 80.4 degrees south latitude on the surface of the moon, which means it's within roughly 9.5 degrees of the south pole of the moon itself.
Right. That's actually close to the South Pole.
Now, it's also interesting. Why would you want to go to the South Pole?
Because supposedly there's plenty of water down in the craters that are at the South Pole, because those craters, the bottoms of them anyway, never see sunlight. And you got to remember, at the temperatures these are, water ice sets up like granite. I mean, it's a rock, essentially.
Now, back, I don't know how many years ago this was, many decades, there was the ideal that was floated around that the water that we have here on the Earth, that it was transported here by cometary impacts.
Right.
So comets, have a very large water component in the form of ice.
It makes logical sense.
And if there was a large number of them, in fact, in the early age of the solar system, from the cratering we see, and you can look at the moon here in this slide, there's craters all over the place, that most of these craters are billions of years old. That was
Right.
done through this part of heavy bombardment in the early part of the solar system, which is really what leftover debris that was left in the protoplanetary disk that didn't go
Right.
into the direct formation of planets
Or wasn't flung out or flung into the sun.
into the sun, and then they end up with the different planets and their moons are going around the planets, orbiting the sun, and occasionally running into this material. So if there's a lot of this material around, the odds of being hit is 100% essentially
Yeah.
over some time
We
period.
call that
right?
the late heavy bombardment.
Yeah, so that's responsible to crater, and for all these craters we see on Mercury and the Moon and so on. And then people say, "Well, where's all the craters on the Earth if that was the case?" Well, what happened to all those craters?
Well, there's this thing called erosion. Tends to wipe things smooth. And we still find plenty of them. There's some big major craters that are a couple of billion years old in Canada. There's the Chicxulub crater that's 65 million years old down on the Yucatan Peninsula. So there are some big craters still around that you can go and see, but most of them get eroded and smoothed out.
And in particular, during the epoch of this heavy bombardment, that was billions of years ago.
Right.
So look at all the plate tectonics that has occurred over that
Some of them
lifetime.
were almost certainly subducted.
Yeah, so that would totally erase out all those craters. And we have the natural weather. If a crater hits somewhere and you have a lot of weathering effect, let's say it hit on the east coast of the United States on a small crater, how long would it take to that to get, wiped out because of the rain and the snow and the wind and so on and so forth? And so eventually those craters, diffuse away, and eventually you can't even notice that
You don't even notice they're there.
Yeah. So that's what happened here on Earth. So the Earth was hit just like the moon.
Right.
So if our Earth had no atmosphere, none of these plate tectonics, we'd have a cratered surface just like the moon has today.
Yep. See Mercury.
Yeah, as an example of that. So this spacecraft is going to land, soft land hopefully, very close to the south pole of the moon. Now, the last time this has happened was an Indian spacecraft, Chandrayaan-2, I believe, was the name of it, and it landed about 70 degrees south latitude. So this spacecraft will land much closer to the south pole of the moon than the one that from India.
The India.
So this will be, as far as I know, the closest spacecraft that has ever landed to the south pole of the moon itself.
Right. And that's a hard thing to do because there's this angular momentum problem that it takes energy to actually get into a polar aligned orbit. And so hats off to them for even if they even pull that off, the maneuvering to get into that orbit.
Now, yeah, so you'd need it would cost more money if you did it directly, because you mean carrying a more powerful rocket that you'd need to, when you got to the moon, either to put it into polar orbit around the moon to make it easier, or initially leaving the Earth, you could get into a moon-Earth type of orbit where you're changing the inclination of the orbit slowly over time with different rocket firings till eventually you're in this polar orbit around the Earth and the Moon system, and then slow down and go into orbit around the Moon in that type of polar orbit.
It's a challenging thing. It takes a lot of added propellant that you have to launch with the probe, if you will. So it's a good project. It's a challenge.
Yeah, you just need the money. That's the thing.
You need the money.
Yeah. So, anyways, we'll see if this works. So let's keep our fingers crossed and knock on wood and all the other type of superstitious things that you may or may not be involved with, and see if it lands. But we'll know on Thursday. So the next podcast, we'll be able to say what happened.
Yeah.
And hopefully we'll have
I
some
thought
cool,
about that, but yeah.
Maybe we'll have some cool images we can show from the surface of the moon.
Yeah.
And
if they release them.
And hopefully it doesn't land upside down like the
or sideways.
Like the one from Japan. Remember that landed on its roof, really?
Yep.
Which was interesting.
On its roof with its solar panels pointed the wrong direction.
Right, unfortunately. So it's amazing that you could land something on its roof and actually survive, right? But
right.
You're in like 1/6
Earth's gravity.
Gravity environments. That's a little easier. And then if things go wrong just before impact, when you're at a slow speed relative to the ground, you need all those things to work.
Right.
And of course, you're building it as light as cheap as possible. So it's not like you have all these shock absorbers all around it, because that would take a lot of weight, right? A lot of mass.
Yeah.
So that would cost more money to get that object to the moon, in that sense. So, yeah, it's kind of interesting how that happens. I don't think that ever happened before, I don't remember ever seeing.
I don't either.
Usually when these things hit, they're like the traditional splat, and that's the end of them, right?
Or they were still rocketing in because, they were informing themselves that they were still 20 meters above the surface when actually they were at it.
Or they missed the object altogether because they got the metric mixed up with the imperial units.
Right,
Remember that?
Yep.
That was one of the flights to Mars, right? Mm-hmm. So we either missed Mars totally, or we crashed, and we're not quite sure, I don't think, what actually happened.
Crashed into the surface.
Yeah. Unfortunately, things like that happens. Why? Because these projects are run by humans.
Yep.
And human error is something we always watch out for.
And by the lowest bidder.
Yeah, right. There's that too. But, there's so many things you have to keep an eye on. People wonder, why is rockets such a big deal now? Well, a lot of it's because of the advancement of technology like computers. Right. There's so much stuff that needs to happen rapidly. Right? It's impossible for humans to control, even from Earth, because you have that essentially a 1 second delay getting the command there, but then another second to wait for the signal to come back. That 2 seconds could be the difference between successfully landing on the surface or crashing, right?
Or crashing.
So
this really comes into play when you've got non-human control. I mean, you don't have humans on site.
Yeah.
When you got humans on site, it's a lot. You can react a lot quicker. So,
Yeah, that's why you need sophisticated computers that are running this software, and the software has to be bug-free,
right,
at least to the point where it's not going to cause any major issues.
right. Or have good exception tables.
Yeah, that's the thing. So
But,
if you're interested in that stuff, get into computer programming, and you can work for these companies. If it's not Intuitive Machines, there's lots of other companies out there that
yep,
that are trying to get into this game of doing this kind of stuff.
unmanned is the way of the future, folks.
Yeah, it's a lot
It
cheaper
really is.
and a lot safer, obviously.
Yeah.
Right? So
A lot less risk of human life, that's for sure.
for sure. Now the other thing, to going on to another topic then that has been in the news lately, is actually related to a supermassive black hole. So this is the paper that you see here. Ordered magnetic fields around the 3C84 central black hole. So
what does that mean, ordered magnetic field?
Yeah, so one of the things that's been not a problem, but I guess something that we need to figure out. Okay, and it's a good thing. When you say it was been a problem, it means it's a negative thing. This is not a negative thing, right? We love problems in science because,
Job security.
well, our curiosity, right? We want to try to solve these things. And there's always been a problem is that when we look at these supermassive black holes, and by that I mean instead of black holes that have a few times the mass of our sun, we're talking about black holes like in the center of our own Milky Way galaxy that's of order of millions of times the mass of the sun to even billions of times the mass of our sun. And associated with these black holes a lot of the time, not all the time, but a lot of the time, is what we call an accretion disk. So it's just a debris disk that's in orbit essentially around the black hole itself. And this orbit, the particles in the disk are in these inspiraling type of trajectories or paths so that the material eventually will cross the event horizon and basically go and disappear from the universe in some sense.
Yep.
They fall within the confines of the black hole and they can't escape because they would need to be traveling faster than the speed of light to get away. Or a better way of thinking about it is space curves in such a way that once you get closer than the event horizon of a black hole, space curves in on itself. So there's no path that would take you away from the black hole.
So you'd have to be able to travel backwards in time to be able to get out.
Yeah, you're forever trapped
Right.
around that space, in the immediate vicinity of the black hole itself. It's one way you think. It's like a bug trapped inside of a paper bag that's closed off at the open end. So the bug can travel on the inside of the paper bag in any direction it so chooses, but can never get outside of that bag. You're forever trapped.
Right.
Now, when we have the debris and the accretion disk that's around or surrounds a lot of these black holes, that debris gets heated up through gravitational tidal forces. And anytime anything with a temperature above absolute zero emits radiation.
Radiate.
So we radiate, right?
Right.
Given our normal body temperature, our internal temperature, we radiate mostly at infrared wavelengths.
Right. Microwave, isn't it?
No, infrared,
It's
which
infrared?
is why that
Okay.
police helicopters, for example,
Oh, right.
right, if they're looking for somebody just ripped off the 7-Eleven on a Friday night, if you're trying to look for people running across the roof of buildings in an urban area somewhere, you have infrared cameras that you
Right.
would use.
And the reason I thought it was microwave is because we had a little small radio dish that we hooked up to a receiver where I used to work. And I would amaze students because I could point it at them and you'd see the needle ding. It would
Right.
detect the microwave emission.
Well, think about the cosmic microwave background.
Right.
That peaks at about 1 millimeter wavelength. That's in the microwaves. Its temperature is 3K.
Fair point. Fair
Right?
point.
And if you're a lot hotter than that, your peak shifts to shorter wavelength.
Shorter wavelengths, which would be infrared.
Yeah, so ours is in the infrared. And so one of the things that happens is that the high temperature of this material gets heated up through gravitational tidal forces, emits radiation, emits light. So we see light coming from the vicinity of the black hole. We don't see the light coming from the black hole itself. Remember, light itself can't escape once you're closer than what's called the Schwarzschild radius, and that's technical term that means, when you're within the event horizon of a black hole, that light can't escape. So it's light that's coming from material outside of the event horizon where the escape velocity is less than the speed of light. So light can escape those regions, and ultimately some of it comes here on Earth, and we can see
Right.
it through our telescopes.
So we can't see the black hole, but we can see the disk around it.
Exactly. And so the other thing, too, is a lot of times what we notice is that there are jets that emanate in opposite direction from near the central region of the accretion disk itself. So the jets are emitting particles and radiation, light, in other words, electromagnetic radiation, from outside of the event horizon once again. But it's always been a mystery how these jets get set up. And we can see the direct evidence for the jets. You can see the jets. I mean, M87 is a classic galaxy that we showed even in one of our podcasts already, where you see an optical jet. And the idea would be then, how do you make these jets? Somehow you've got to collimate the material, that is, have it come out almost like in a nice narrow column. You think of light coming from a laser pointer, for example. And we know it has to do with magnetic fields. And these environments are a lot of energy, so stuff is at a high temperature. Most of the material is ionized in one form or another. So we're talking about charged particles, a lot of charged particles around, like electrons. And then you have magnetic fields. And the idea is charged particles are influenced by magnetic fields. In fact, in general, charged particles spiral around magnetic field lines, and they can emit something that we call, to be technical, synchrotron radiation. That's just it's different from the normal thermal radiation, as we would say, that just due to the fact that some object has a certain finite temperature, like us emitting in the infrared or so on and so forth.
Bottom line, a charged particle that's moving will emit radiation when it accelerates, and a change in direction is an acceleration.
So a big mystery, and it's not totally solved even today, is how does these jets initially get set up, and how do they maintain their structure, if you like, over apparently long, long periods of time. And so this study is looking at that, trying to look at very high resolution, very fine detail of the jet that's in this particular galaxy, which is known as NGC 1275. And the black hole itself emits in the radio. It's a radio source, so that's why it's in the third Cambridge catalog of radio sources. And how do I know that? That's what the 3C stands for. 3 means the third catalog, C meaning Cambridge. Okay, and so it's listed as number 84 in that catalog. But that just refers to the supermassive black hole at the center. The galaxy itself is NGC 1275. It's about 257 million light years away from us.
Okay, so neighborhood.
Yeah, that you think that's like a long ways away. In other words, the light that enters our telescope tonight from that galaxy left that galaxy 257 million years ago. Now, where were you, Robert, 257 million years ago?
I think I was in the late Triassic grazing on some ferns.
Yeah, you're not even a twinkle in somebody's eye at that point. It's so far back in time.
Right.
I mean, humans weren't even around then. I mean, this is in the period of the early dinosaurs, if I'm not mistaken, right?
And that's exactly right. That's why I was saying late Triassic, I'm not sure that it's Triassic, might be Jurassic, but yeah.
Now, if you want to understand how these jets are created and how they maintain themselves, one of the ways to attack this problem is to obtain very, very high resolution images of the jet, to try to understand its structure in detail, to see things that otherwise you can't see at much lower resolution.
Right.
And that's what this paper is all about. In fact, Robert, if you go to the next slide, we'll get an idea of what the improvement is of the resolution looking at various wavelengths. So looking at the slide, so it's a mosaic of basically 4 views of the region near the jet from the supermassive black hole in the heart of this galaxy. If you look at the one that's on the leftmost side, sort of the upper left a little bit, that's at 20 millimeter wavelength. So this is from the VLBA. It's a very long baseline array. And you can see the structure in the jet. So the area where the jet's launched from is sort of that brightish lobe or spot in the bottom part, the lower part of the image itself that's on the left. If you go over to the right a little bit, the next one is from the same instrument, but it's tuned to 7.0 millimeters. So this is a European paper, and so their desmo is a comma, right? That's the standard format here. So 7,0 just means 7.0 millimeter, and that's the wavelength that the observations were done at. And notice that you can see much sharper detail.
Right.
So the shorter wavelength gives you...
Shorter wavelength gives you better resolution.
Gives you better resolution.
Detail.
In fact, you can see that, well, not to get technical, but in astronomy, we talk about what's called the diffraction limit of a telescope. And that typically means if you take 2 objects that are emitting light, let's say 2 stars, And if you were to magically move them closer together, at some point they no longer look like two independent sources of light. They're sort of merged together and you think there's only one source of light.
Yep.
So you can calculate what is the minimum angle between those two sources of light such that you can just barely tell they're two independent sources of light and not one. And that's the diffraction limit of the telescope.
A more concrete example for most of us, think a car's headlights. At a certain distance, you can't tell if it's just a car that has a headlight out or if it's just a car that's that far away because the two headlights are too close together for you to tell if it's one or two.
Right. And that relationship, that from the point of view of physics, that describes the diffraction limit of the telescope, how best you can do, what is the finest detail you can capture. And this is, of course, excluding the atmospheric effect and everything.
Right.
So imagine a space-based telescope, for example. That diffraction image, the diffraction limit, the smallest angle, the minimum angle of separation to barely tell there's two sources of light, goes like the wavelength divided by the diameter of your instrument.
Right.
So that means if the instrument is the same, like in the case of these two images, the VLBA, that means the shorter the wavelength, the smaller is that diffraction limit, the more finer details you can see.
Right.
And that's exactly what we're seeing here in this slide.
So the two VLBA images, going to 7 millimeters basically improved the resolution by about a factor of 3.
Yes, exactly.
So
Everything else being the same, you're only changing the wavelength.
right.
And then the one that's in sort of the one that's to the right of that, so the third one from the left or the second one from the right, depending on which way you count here, it's taken from a different instrument. And notice it's at 3.5 millimeters. So what you're looking at there, though, is just that bright blob that's at the top of the image that was one taken at 7 millimeters. So if you expand that bright blob at the very top of the one that's directly as the second one from the left, and you expand just that top part, you'll get that image that's the third one from the left, taken with the GMVA at 3.5 millimeters. So now you can see details in that blob. Now, if you take that blob itself and look at it with the Event Horizon Telescope at 1.3 millimeters, you get the image that's on the far right. And that's the exciting news to me in this study.
The jet is made up of blobs.
Now, notice, this is the same instrument that was able to resolve the supermassive black hole at the heart of M87, the one that has that optical jet, and also the black hole that's in the center of our own Milky Way galaxy.
And they're working on others.
And they're working on others. In fact, they're adding more telescopes, radio telescopes, to the array to allow them to make even finer type of images of whatever they're looking at.
The baseline of this telescope is essentially the side of the Earth facing the target, because the telescopes are spread out across the entire face of the Earth.
So even in this bright blob at 1.3 millimeters, given the resolution of the Event Horizon Telescope, you'll notice that there's really, three sort of separate regions. You have E, C, and the one on the W one there on the far right. And so we're starting to see at least some coarse-grained structure in the very little tiny knots that are embedded within these jets. And like I said, the more details you can see, the better things are. Now you might wonder then, what's the size of these blobs on the far right from the Event Horizon Telescope? There's a bar there that says 250 times R sub s, and R sub s is that Schwarzschild radius, which is a measurement of the radius of the event horizon if you have a black hole that's not rotating. So non-rotating, non-charged black hole.
See, I would have thought it was Saturn, the radius of the orbit of Saturn.
It's a Schwarzschild. And it's important why the Schwarzschild is because we're talking about supermassive black hole, environments here. And so it makes sense that you would use that as sort of a way to figure things out. But in terms of the angle, now this is interesting. What is the highest resolution angle that we're getting here in the Event Horizon Telescope to be able to resolve these three circular type of blobs? We're getting a resolution, now get this one, Robert, of 50 micro arc seconds.
Holy crap. Oh my.
50 micro. Now what is 50 micro arc seconds? Well, here's a way of thinking about it. If you took a dime, a US dime, and you held it at a distance away from you of about 49,000 miles, with this resolution, you could make out then that the dime was not a point source but had an extended size to it.
Wow.
You could resolve the diameter of a dime.
Okay.
49,000
How many
miles
observations and how long did they observe to get that kind of resolution, though? Because
well, that's it, right?
wow.
Yeah. So this is the best, essentially, you're on the edge of the best we can do with present technology and the way to set up. Of course, as you mentioned, you can add more radio telescopes to the array. Different points on the Earth helps. And the other thing in going in the future, you can imagine we can send arrays out into space. So we can observe, with an array in space, and that increases the baseline and can provide effectively a much larger diameter instrument, and therefore, you can make the diffraction limit.
I think
smaller.
there's even a small space interferometer that's even on the slate for being launched, isn't there?
And we've had ones in the past. Well, we had small radio telescopes, I should say. I mean, the Soviet Union, Russia, back in the time of the Soviet Union had launched one. And even Sweden had put up a small radio telescope. So there have been small ones. But yeah, the future is bright. I mean, especially what we really need is the ability to get our instruments up there cheaply.
Right.
Because when you talk about an array, what we mean is collecting signals from multiple radio dishes, if you can think of it that way, or multiple radio antennas. So you want to do several launches to get that equipment in space.
Or multiple optical instruments, seeing how in space you can really get the beam path, which is critical to getting any information out. But that's another story.
Well, I don't know why I thought about this, but remember, Robert, the line from the first Alien movie, in space no one can hear you scream?
Right.
And so if you spend a lot of money, no one can hear you screaming from all the money you spent.
Right.
Especially if the rocket blows up and wipes out all your stuff. Right?
I don't know. I think they'd hear me scream.
But it's amazing, we're pressing the technology to the very limits. The envelope is being pushed out as far as we can essentially get.
Which is where interesting things happen. So
and so
this is something we should be doing.
It's going to be amazing in the future when we improve this type of instruments to see what we can actually see in these type of extreme environments. And to further our understanding of, like I said, like jets, for example, that it's around these vicinities of these supermassive black holes.
Right.
Now, talk about pushing technology.
Woo!
There was recently then a news item that came out, if you want to go to the next slide, please, Robert, that talks about the future of basic particle physics. And this future is basically the next generation of the Large Hadron Collider. Now, the LHC, and you can see a diagram here, a cartoon representation of what some particle physicists are proposing, especially in Europe, is the construction of what they call the FCC. It sounds like a government body that regulates what you broadcast over the air. But in this case, it means the Future Circular Collider. Now, that name is going to change if they decide to build this, right? I mean, just the first word, you would have to call it the present.
The PCC.
Right. So anyways, what is this FCC? What is it all about? Well, it is going from the Large Hadron Collider, which you see there illustrated, into a much larger collider, a greater circumference. In fact, the propose is to go from the size that the LHC is now to about 3.5 times greater in terms of circumference.
Okay.
And so we mean getting up to values of about 91 kilometers in circumference. And you can see the difference in size there. So it's it's on the border with France and what is it? Switzerland.
Die Schweiz.
The LHC. And so what is the LHC? That's the Large Hadron Collider. That's the instrument they used to find the Higgs boson a few years back. And so it is our most energetic collider that we have in operation right now in the world. It smashes particles together, which are two protons. A beam of protons circulates in one direction, another beam of protons circulates in the other direction, and then they allow the beams to cross. What you don't do in Ghostbusters, right?
You do cross the streams.
Yeah. And so when you cross them, you essentially would have, let's say, one proton in a direct collision with another proton at energies, the maximum energy around 14 TeV, tera electron volts. Okay.
That's a lot of energy on the particle level, folks.
And this new proposed instrument would smash particles together like protons at energy scales of about 100 TeV. So in other words, about a factor of 10 times greater in energy.
Okay.
Now, will this thing get built? Well, this is an interesting discussion. Why is it an interesting discussion? Because there was a lot of money spent on the LHC on the order of, let's say, 10 to 14 billion dollars. Whether that number's in euros or in US dollars, it doesn't matter.
It
It's
doesn't
still
matter
billions.
at that scale.
It's billions of them, right?
Right.
So it's a lot of money. And one of the goals of the LHC was to find the Higgs boson. And they found it. Great accomplishment, won the Nobel Prize in Physics for that discovery. Now, what has been discovered since then, Robert?
I can't think of a bloody thing.
That's it. That's the problem. That's the problem. This thing could potentially have detected.
The supersymmetric particles that.
Okay, so supersymmetric particles, and you might wonder, what are supersymmetric particles? So these are particles that have been proposed through various arguments and we won't get too technical, to deal with symmetry. And in physics, symmetry is everything.
Right.
Okay, symmetry, a lot of things can be understood from the point of view of understand symmetry. For example, take a circle and rotate it by a random angle. And when you look at it, it looks exactly the same before you rotate it. So
Right.
it has rotational symmetry, right? In that sense. Or you can think of other different objects, the way you move them, or all this kind of different shapes and so on and so forth.
Crystals are crystals because they have symmetry.
Yeah,
for instance.
right. And so there's lots of things you can talk about, and it's not a new topic. It's been around for many, many, many years. And so out of the sort of our understanding of particle physics, the Standard Model is this add-on to the Standard Model, where for every particle there is sort of a supersymmetric particle. And so you would have, for example, a particle to the photon would be the photino. A particle to the Higgs particle, the Higgs boson, would be the Higgsino.
Higgsino, yeah.
Right?
I love that word.
And the the supersymmetric particle to the neutron would be SN, sneutrons. Or to the electron would be selectrons, these kind of things, right? And
Right.
they'd have their host of antiparticles. So antimatter to the electron is the positron, so there would be an antiparticle to the selectron, the antiselectron. So there's a whole new family of these supersymmetric particles that may or may not exist. Now, if they do exist, that is a good thing from the point of view of people who spent a lot of time working on things involving supersymmetric ideas, like string theory.
String theory,
Right.
basically the Standard Model, as it holds right now, kind of requires there to be these supersymmetric particles.
Now, in the old version of string theory, it was super string theory. And the super came from the supersymmetric particles need to exist for this theory to be realized.
Right.
And so string theory, and a lot of you have heard, what is string theory? Well, it's a way of, in the modern day, a way of thinking about, of merging all of the fundamental forces of nature. So all of gravity, all of quantum mechanics, all the forces, right? So you can think of, there are four fundamental forces in nature. There's gravity, there's the electromagnetic force, there is the strong nuclear force, and the weak nuclear force. All four of these can be merged into one, which we call the TOE, the theory of everything. And so there's some way of unifying all of these fundamental forces into one so that you could write down an equation. In physics, we could write down a Lagrangian that would have contributions such that we would unite all of these forces together into one.
And from everything I've read, maybe this has changed, but we've had great success at merging three of them, but we can't get gravity to come along for the ride.
Yeah, so think of the 1800s, right? Along comes Maxwell and essentially unites electricity and magnetism. And that wasn't far off in terms of that unification. Why? You can do simple experiments. I could take a battery, take any battery you like a AA battery, attach a wire to one end, and then have a compass nearby. And when you attach the other end of the wire to the other end of the battery, you'll notice as soon as I make the connection, then the compass needle will shift, will move.
Right.
If the wire is near the compass but not touching it. Why? Because that flow of electrons in the wire when I made the connection generates a magnetic field, and it's the magnetic field that deflected the compass needle.
Right.
So there is an inherent connection between electricity and magnetism. You take a bar magnet, have it spinning inside a coil of wire, a wire,
And you generate an
and
electric
you can
current.
generate electricity. That's how generators are formed that way, right? So we know that electricity and magnetism are not two so separated phenomena that are somehow unrelated to each other. We know they're directly related because of these early experiments that were done, 100 years ago and more, right? And so the unification of electricity and magnetism was written down from the point of view of equations, from the theoretical point of view, by James Clerk Maxwell in the 1800s. So from that moment forward, it's electromagnetism, not electricity and magnetism being separate. So this whole process of unifying these forces is something that even Albert Einstein got in. He tried to unify gravity with the electromagnetic force, and he failed at that. He passed away in 1955. And one of the reasons for it is there was a lot of things that he didn't know about, and a lot of things that came along after his passing that we know about today that would have helped in that process of trying to unify these forces. In fact, I believe it was the 1960s into the 1970s that we unified the electromagnetic force with the weak nuclear force. So we have the electroweak force.
Right.
Stephen Weinberg, Sheldon Glashow, and there's another individual.
I don't remember the names, so
Yeah, a person that was from Pakistan, that Abdus Salam, that the three of them jointly won the Nobel Prize in Physics for the discovery of the electroweak force, right? The unification of electromagnetism and the nuclear weak force. And then there was adding together then the strong nuclear force. And this is what grand unified theories were all about in the late 70s into the theories.
That's the guts of physics.
The gut theories. And when you have a theory that seems to unite these forces, of course, you want to make predictions.
Right.
And so we can go out and make observations to see if they're consistent with that theory or not. If it's not consistent, you need to modify it or reject it completely. And so one of the byproducts of these type of grand unified theories was that the proton is unstable and should decay. Well, people have been running experiments since the early 80s, I believe it was, looking for proton decay. We haven't seen any. So the early models said that the time scale that protons decay is short enough that we should have seen them in those type of early experiments. We didn't see it, so those early simple theories are wrong. You can throw them away. You start with the simplest one, Occam's razor, and then you build up the complexity. So now the grand unified theories that have not been ruled out are the more complex one, I think it's fair to say. Right. Whether or not they're legit or not, who knows, right? We're still checking out with experiments.
Well, we've got to do experiments and try to find out.
Now, the other thing that's been a great push since the 1980s is trying to unite all of the forces, including gravity. And these are the so-called string theories. And the idea there, if you get into a lot of trouble if you think of particles as being point-like objects, right, because you run into infinities. Because you're looking, when a point-like strictly would mean something that doesn't occupy any space at all.
Right.
And so that becomes problematic, right? How can you have a certain charge confined to zero volume? If you take anything divided by zero, you should get infinity as an answer.
Right. So you all of a sudden start getting infinite densities, infinite energy concentrations, and they're called singularities.
And that's a bad thing, of course.
Yep.
To avoid that, people come up with the hypothesis, well, maybe instead of point particles, you think of little loops of string, vibrating strings. And the way that the string vibrates, these energy strings vibrate, determines the type of particle. So a neutron string would vibrate at a different way than one that's responsible for an electron, and so on and so forth. And that got modified eventually so that we don't think so much of strings, but now we're into these membrane type of things and so on. And we're up to 10 dimensions of space and one of time. So we're into 11-dimensional space-time and all these kind of things. And then people argue, well, if space has a 10 dimensions, let's say, I'm aware of 3, what about all the other dimensions? Well, they're wrapped up amongst each other. So you take one dimension, if you wrap it up into a small space, you're not sensitive to that dimension. It's curled up on itself. It's like a bug walking along a wire. It only can go in one direction. It can't walk around the wire. So it's unaware of that other dimension. It's only aware of that one dimension, which is the length of the wire itself as the little bug is crawling down it. You see that kind of idea. So you can kind of hide these extra dimensions, right, which makes them difficult to detect. And that's why we're not aware of them in our ordinary day life type of thing. But a lot of this hinges on the existence of these supersymmetric particles. That's why it's superstring theory, right?
Right.
So whether or not these particles exist is a big deal in physics. And so the LHC was designed to produce some of these supersymmetric particles. The energy of the collision can produce particles. And that's really Einstein's famous equation of,
Oh.
What's his famous equation?
Uh,
You remember? What is arguably the most famous equation of all of physics, Robert?
let's see. E squared equals m squared c to the fourth plus p squared c squared.
Boy, you went really into it, didn't you?
Yeah. Okay. So it's E equals mc squared.
Yes, we'll keep it simple here. Okay?
we won't add in the momentum component.
Yes. So E equals mc squared. We won't think about rest mass versus
Right.
momentum. And so anyways, so if you have energy, that energy essentially can create particles. And with more energy, you can create more massive particles.
And these supersymmetric particles, if the predictions are correct, should be very massive.
In fact, if some of the predictions are correct, they should have been created in the collisions in the Large Hadron Collider,
Right.
and they would have been announced by now. We would have seen the signature of the existence of these supersymmetric particles. We haven't seen any.
Right.
And this is at the highest energy that the instrument can run, at the present setup. Still no sign of these particles. Now, you could say they don't exist. Okay, that's one way of explaining it. The other one is, well, maybe we got it wrong in terms of their properties. Maybe we need to go to much higher energy, a la the FCC, you see?
Yep.
If you go up to 100 TeV, tera-electron volts, maybe we'll find lots of these supersymmetric particles. And so we just don't know. But the other thing could be, though, is that you build this instrument and you still don't find them. Then what do? Build an even larger one. Every time you build one of these instruments and you're making it larger, what does that mean? That's costing you a heck of a lot of money.
Right.
So there has to be, if you like, the will of the governing bodies, in this case of the European Union, which runs essentially CERN here, the International Particle Collider Institute in Europe. There has to be, these European countries have to be willing to be able to hand over that amount of money to build these detectors. Whether or not they find anything, who knows?
Who knows?
So it's something like a crapshoot in some sense.
And at some point, you've got to say, are we barking up a dead tree? I mean, that's, to me, that becomes the real question is, well, I mean, getting the money for it is one thing, but you've got to ask yourself at some point, are we just wrong?
Right. So we'll see whether or not this gets accepted and actually gets built. Who knows?
Right.
But wait and see. But there's a lot of potential discoveries that are left to be made here, but we just don't know, right?
A lot of technology that needs to be designed to overcome the obstacles of creating this thing. So to me, that the economics becomes a secondary issue simply because the economic benefits that will come out of solving these problems are going to counter any costs in the long run.
Now, speaking about technology again, Robert, you want to go to our next slide?
Sure.
There's been an interesting paper that just came out recently regarding the potential of life underneath the surface, that is in a subsurface ocean, of the moon Titan, which is the largest moon around the planet Saturn. Now, this paper argues that in order for life to arise in some type of subsurface ocean, there must be a way of bringing organics into that ocean, into that body of water. One way to do it, of course, is through a lot of collisions, let's say, with comets, for example. We know that asteroids and comets have a lot of the basic building blocks of life associated with them because we've analyzed these things directly.
Right.
I mean, there's just recently in the news where NASA says they acquired twice as much material on the Bennu mission, right? The Bennu asteroid, right, on that OSIRIS-REx mission. So we've actually brought samples of this material back to our laboratories here on Earth. And we know the basic carbon-based or type of life, organic material that could potentially allow life to arise exist on these objects. Now, if they crash on the surface of Titan and some of that material gets down into the ocean below the surface, that could potentially, over enough time, allow life to form. Maybe. So this paper basically is arguing that given the setup and running simulations, that they don't see that there has been enough delivery of these organic building blocks to that subsurface ocean on Titan, so that the probability of life to exist is a lot lower than it was otherwise.
Right. Well, I can see that. I mean, getting something through, Titan's got a very thick atmosphere. So it's just like on Venus, we don't see a whole lot of impact cratering from what we've seen of its surface. I would expect the same issue on Titan. You're going to have very few objects that can penetrate the atmosphere, much less punch through the icy crust.
Now, of course, if there's some way of bringing up this kind of material from deep in the interior, that's another story.
That's another matter entirely.
That could easily reach this area where the ocean is presumably at. But from the outside, it doesn't look like there's enough support of bringing in stuff, ex situ, I guess you would call it, to the
I like that term,
to the subsurface ocean. And that's one of our goals, right? Is that in the future we would go to Titan, either unmanned it at first, of course, and then eventually manned it, and drill down through the icy crust hopefully into an ocean, and could send probes like little tiny miniature subs, right? Some nano subs that would go down there and explore the ocean, maybe looking for signs of life, and obviously figuring out what it's made up of, its composition and so on, all its properties. So that's something that's on the radar, if you like, in the future to do. But when we talk about Titan itself, Titan is one of these interesting objects because we don't have to dream at night about what it would like to be on the surface of Titan. We actually have done that.
Yep.
And this involved the Cassini mission. When Cassini went into orbit around Saturn, one of the things it brought with it was a probe, the Huygens probe, which was built by the European Space Agency. And the probe was designed to actually land on the surface of Titan, to take images of the surface, and to sample its condition, its atmosphere, and so on and so forth, to give us a little idea of what it's all about. So as you can see here in this artist's conception, this drawing, then the probe came in on a heat shield. Titan does have a thick atmosphere, so you do have to have a heat shield. You're coming in fast enough. But then notice when you get to lower enough level and you slow down enough, you don't have to worry about the heat shield. Then you can pop open a parachute and have this lander gently land on the surface of Titan itself and make the measurements. In fact, this happened back in 2005. And since that time, of course, the scientists pieced together all of the direct observations that were made by the camera on board the lander of what it looked like as it was landing on the surface of Titan and so on, and what the photographs looked like that had taken when it was on the surface of Titan. Now, Titan's under these conditions such that hydrocarbons may be in the triple point of hydrocarbons, right? Where you could have methane lakes.
Yep, methane ice, methane lake, and methane gas.
Yes, exactly. And so we just don't know. That's some of the idea. In fact, we see evidence of dried up tributaries on the surface of Titan. We've seen, glints of sunlight that's reflected near the polar regions that look like light reflecting off a lake of some unknown material, like methane, maybe. In fact, if it is methane in the future, we could use Titan as a gas station.
Absolutely.
To power up our rockets and to further explore the outer solar system without dragging all that stuff from the Earth.
Don't need to drag fuel along. Yep.
Exactly. So it'd be a great thing. So, Robert, we do have a clip of that movie that was generated by NASA and European Space Agency about Huygens landing on the surface of Titan. This is real data. This is not made up. So let's show that right now.
Well, this part of it is made up.
Yeah, this part. So this is the Cassini spacecraft, and showing you the Huygens probe that's piggybacking or attached to the side of the spacecraft. Here is the release of the Huygens probe before Cassini went into orbit around Saturn. And the probe itself has its own independent trajectory now, taking it to Titan. So you can see Titan there below it. It's coming in the heat shield first, of course, so it's going through the hot phase of the reentry.
And now we start seeing actual data.
So this is actual data. So this is all compressed. This is 2.5 hours of data compressed into just a few seconds. So you can see the surface of Titan itself as you get through the layer of haze and so on. If you look carefully, you can see different areas where it looks almost like tributaries here on the Earth, right up
see it like a little lake up there in the upper right. And so it comes in.
So you can imagine this is a view you would get if you were landing a spacecraft on Titan. You would see this kind of stuff happening right before you look at the windows. So there's the dried up riverbeds are potentially made of methane, so liquid form.
We call it
flowed on the
dendritic
surface
texture.
at some time,
And you can tell that it's something of a fisheye lens to give you a wide angle.
Yeah, that's just like I said, these are real images here. This is not made up. You can see beautiful tributaries everywhere. And we're going down through this layer of haze off to one side here. And there's the surface of Titan as we're descending. Huygens has landed.
Yep.
And you watch, there's a shadow of the parachute. You see the dark spot? That's the parachute slowly floating down to the surface. You can even see the shadow of it. It's amazing when you think about it.
Oh, yeah. And I like pointing out that those rocks that you see are actually almost certainly water ice. That, like I was saying, it's frozen to such a hardness that it's like granite. It's like rock.
Now, notice that the perspective, if you go to back to the original slide there, the perspective of that is that Huygens is really close to the surface. So it'd be like you're laying on your belly looking around at the scenery.
Right.
That's kind of the view you get there. It's not like you're standing up on your 2 feet, several, 5 feet above the surface at your eye level or something, or 6 feet, depending on how tall you are, looking around at the surface of Titan in this case. You're looking at it from the ground level. So you get this kind of weird perspective anyways. But you can just imagine trying to land on this, or what it'd be like to roam on the surface of Titan. It'd be amazing when you think about it.
Oh, it'd be,
In fact, we are planning to do just that. So this is a proposed mission that so far has been funded through the various stages in the process of what it takes, the many, many years that you need to put together a team of scientists and engineers to propose some project and go through all the different stages to get it fully funded all the way up until launch time. That's a long process. So this is one of those projects. It's known as Dragonfly, and it's going to go essentially a helicopter, a drone, for lack of a better word here, that it will be landing on the surface of Titan and then explore Titan. It's not going to stay in one location. So this so far it's due to be launched in July of 2028. So it's actively being built today. It's supposed to land on Titan, if it does make that launch date, land in 2034. So we'll still be around, Robert, hopefully at that time.
Woohoo, I'll be here.
That's only, quote unquote, only 10 years from now.
10 years.
So we should be able to make that.
And I love the instruments. These are some great mass spectrometer, gamma ray and neutron spectrometer, geophysics and meteorology packet. Oh, heck yeah.
Yeah, so
I'm all for this.
Yeah, so you can see the instruments then, as you just mentioned. So it's going to do detailed scientific analysis of the surface of Titan. So we're going to get some incredible information coming from Titan itself to get an idea. Number one, is there life on the surface? You may see evidence of that. Who knows, right? But probably what you're going to get is you're going to be able to analyze in detail the properties of the surface itself.
If you find lakes, what are they made out of? Are they methane? Are they ethane? Are they a combination of the two?
Now, it's interesting that the Dragonfly spacecraft is good. The mission should go for about 10 years or so, and it can fly, a lot. It can be reached. So you think about the energy requirements. So how's it geared up? Well, if you look on the panel on the right, you can see some propellers. Notice it's double propellers. Now, the atmosphere on Titan is reasonably thick. It's a lot thicker than Martian atmosphere. Remember, we had Ingenuity, we talked about the last podcast, that was flying around on Mars and doing different imaging and so on. And so it's a little easier on Titan itself. It has a double propeller, and there's 4 of them. So it's a quad type of situation here.
It's a quadcopter. Woo!
Yeah, exactly. and so there's instruments even built, a sampler that's underneath the landing pads of the spacecraft itself. If you were to flip this thing over and look, there's a probe that comes down and actually sample the surface material.
Nice.
So that's going to be really interesting. I mean, it's built for scientific analysis here, as it should. The interesting thing that I find, number one, is you look at that sort of circular thing that's pointed up, on a slant, on the top of it. That's, if you look at the panel, especially on the right, that's the high gain antenna. So it's direct communication back to Earth. There's not going to be an orbiter in orbit around Titan or Saturn that somehow would relay the signal. No, it's a direct high gain feed back to Earth, which is really amazing.
Well, that's amazing. That's going to be a first.
And the reason you need it, the reason why they have it, as part of the reason, is it takes a lot of power to run these things, right? So what's the power in this? It's not solar panels, which ultimately maybe you get dirt on or stuff. What it's powered by is these radioisotope thermoelectric generators, the same things that powered the Voyager 1 and 2 spacecraft, for example. So in other words, it's the decay, usually they use plutonium, the natural decay of plutonium releases heat, and that heat through a thermocouple is converted into electricity. In other words, this sucker's nuclear.
Woo! Can it get up to, what is it?
1.7 gigawatts? Back to the Future.
Yeah. Then we just got to get it up to 88 miles per hour. Sorry, folks.
But this thing carries a powerful power plant. It can generate a lot of electricity, which means it can power then the transmitter to send that signal directly back to the Earth. That's what I'm getting at. Plus power, of course. It has a lithium-ion battery into it, which everything does nowadays, it seems like. So this power plant then can recharge that lithium-ion battery during the nighttime when it's not flying around and get ready to fly the next day if they so choose to do so, to fly around to different landing sites and so on and so forth. So this is going to be extremely amazing if they can pull this off, safely land on the surface of Titan, and then start flying around a different, almost like you think of it as a bumblebee that's going from flower to flower to flower. That would be the dragonfly in this case, right? And it's going to be amazing the amount of science we should get back from this mission. Now, if you're interested in this and what will the future hold in solar system itself? Don't think of anything else. Just think of our own solar system. What type of exploration can we do just today if money was unlimited, right? And you can send all this advanced technology. We have drones and stuff. You don't even have to send people into these harsh environments. Send robots, right? So you can imagine the amount of discoveries that we can make just on what we have available today if only we had enough money to launch all this stuff.
And that requires just having the will, the desire to do it.
But ultimately, you need knowledge.
You need knowledge.
How do you get that knowledge? You come to places like here, the University of North Dakota, and you take classes that's in math, in physics, in any type of STEM field you like. And of course, we also include the arts. Somebody's got to write about this stuff.
Absolutely.
Somebody's got to communicate the science to the general public. Why? Because in countries like where we lived in, it's the people that determine where the money is spent. If you want money spent on these projects in the space program, then you need to get a hold of the government officials and let them know what is the advantage of spending this type of money. To do that, you need to be able to communicate.
So, we're big fans of the arts as well, but yes, come join us. Come see what we've got.
Now, Robert, our next podcast will be Tuesday, February the 27th, the last one in the month of February already.
Wow.
It's going so fast. It's amazing when you think about it. And we always leave you with a quote. So today's quote is related to astrobiology, fittingly, because we're talking about Titan and potential life on there, or maybe, the building blocks of life. So the quote today is from David C. Catling from his book that is about astrobiology. The quote is this: "However life started, once established, it persisted for over 3.5 billion years and evolved from microbial slime to the sophistication of human civilization."
That's a good one. I like it.
Thank you very much for watching.
Have a good night, folks.